हो गया ना? ठीक है. Good morning to all. Thank you for the introduction. So I will be covering two sessions: design of barrages and design of dams. So first I will try to start with the design of dams, and it is completely one presentation only. So at the end we will try see about the design of barrages and weirs. Okay. So I hope you have seen in last 3 days you have learned some concepts of related to dams. So I will this complete session will be interactive type. It's better if you answer some questions whenever you have any doubts. You can ask on that particular slide. Okay. So can anybody tell what are these types of dams? वो pointer है? ठीक है. हाँ. ठीक है. So can anybody tell what is this first dam? What is the type of the dam? First, the screen is visible, right? Clearly, and the voice is clear. Yeah. So please tell what is this type of dam? You can tell loudly. Wrong answers also no problem. You just tell whatever answer you get in your mind. Yeah. This is concrete dam, and what is this dam? Yeah, and this? No, dam. What is the name of this dam? This is a very big dam in India. This is Tehri Dam. So Tehri is India's largest dam. So Tehri is rockfill dam. So this is concrete dam. This is earth dam. This is rockfill dam, and this is masonry dam. This is concrete face rockfill dam, and this is arch dam. So we'll see the differences basically here. So we all know concrete is completely concrete, and the difference between concrete and masonry is a old dam. So nowadays we are not using any masonry dam. So just upgradation of this masonry dam is concrete dam. So now these three dams will be of same category. So this is, you can see, this is a failed section. This is the dam in Rajasthan, Garada Dam. So in the first filling only it got failed like this. So if you see the section, it's completely same material, right? That is why we call it as a homogeneous earth-fill dam. Whereas this is rock-fill dam. That means in the it is completely fine material, right? So this is replaced with some large size boulders, and in the center they will be having clay material. So this is rock-fill clay covered dam, and further addition to this upgradation to these dams is to minimize the section. You can see the slope. This is almost 3 times 3 horizontal, 1 vertical type. So to reduce the material quantity, we can have this concrete face in upstream side. So that is called concrete face rockfill dams. That also I will explain in detail in the coming slides. So now we will see the names. So like already everybody told, concrete and earthfill dam, rockfill dams, masonry, CF40 dams, concrete face rockfill dam, and this is arch dams. So arch dams in India also we are having only 1 or 2 only, because for arch dams design is a very issue, and the second thing is we should have this strong abutments for arch dams. So now like I explained, right, concrete face rockfill dams. So it will be like rockfill dam only, but in the upstream phase they will be having some concrete layers, concrete panel. So this is one more type of dam, roller compacted concrete dam. So in roller compacted concrete dam, the difference is that in concrete, so in the concrete dam you can see here it will be like blockwise, like in the vertical it is a divisions, every 15 meter or 20 meter it's a blockwise division, whereas in RCC dam layer wise, just like earthfill dam, right? We just we'll lay one layer and roll it, and then one more layer. Like if you see in this section, they will have first layer, then roll it, then second layer. Like that the construction will go. Whereas in concrete dams, it is blockwise construction. So this vertical 15 meter is a separate block. This second 15 meters is a separate block. This overflow What is this? No, what is this? Piers, okay, then exact what is, so this is non-overflow block, and what we call this arrangement, complete arrangement? Spillway. This is spillway. Why spillway is required? Yeah, if there is for any dams, obviously there will be some inflow. So to pass the inflow whenever we need it, so we will have some overflow kind of arrangement. So generally that is called spillway. So that will be gated, ungated. If you see here this masonry, there is no gates. So water will go over this dam top. Like I told, so in concrete dams we will be having these block-wise constructions. Like vertically we will raise 15 meter blocks. I will just draw whenever I go to that place. In RCC, what we do, just like a earthfill dam construction only, we will place layer-wise construction. That cement concrete will place 300 layers, roll it, and go to the next layer. So that is the difference between normal concrete dam and roller compacted concrete dam. You can see these steps, right? So these are the different layers. So first they will place this layer, allow it for some time, then go for the next layer like this. So these are the other type of dams. Rubber dam, generally the limitations will be height limitation, maximum 2 to 3 meters only we can have the height, because whenever needed, whenever we want to store some particular water or to allow water into the channels, canals, we will inflate this so that it can rise like this. So 2 to 3 meters head we can create, and we can allow this water to flow like that. So now we will go into the design steps. So in dam design steps, the first step is water availability. So by now I think you know how to estimate water availability and dependability. Everybody is clear about how to find out the water availability and dependability. So what is dependability? Anybody? Anybody can answer? I think you know this at least by now. What is dependability? That's why I told my class will be interactive type, so you can answer wrong answers also, no problem, because we are all learning only. Dependability is what not taught in this week. How to estimate dependability? Availability, how did you estimate? So generally nothing, like we will be collecting data. CWC is having so many GND sites, gauge discharge sites. First we will try to collect their data, and we will see based on their data we will estimate yearly basis, monthly basis. So dependability means I will just see if it is. So you can see dependability. These are the different dependability values, like domestic supply 100%, hydropower 90%, and irrigation 75%. So what is the meaning? At least now you should tell. What is the dependability?
Amount of water needed for.
Yeah. So if you are designing a project or any water resource project for suppose let's say domestic supply, so you should see that water should be available for all the 100 times. That is the dependability, because every day you should have some at least water supply, right? So that is why, suppose let's say if your town is having some 1 lakh people, so we have the 150 liters per day, right? So just multiply with it, you will know the volume. So that much volume you should able to provide on the daily basis. So that's how you will calculate water availability. If the water availability suppose let's say some X value, that should supply 100% times throughout the year. That's how you have to plan the projects. So whereas hydropower 90%, that means even 90% time water is available for that hydropower, that is also okay for hydropower. Irrigation we will check 75%, that means 25% failure also we will allow it. So irrigation, suppose let's say we are planning for 100 days of irrigation, even if you can provide for 75 days of water to the irrigation, that is okay. So that's how you design the project. First you estimate the total water required for 100 days, then even you can provide for 75%, 75 days, that is the meaning. So that's how you can work out the dependability. How do you work out the dependability? So you can see here, this is in terms of hydropower, like for hydropower dependability calculations. So first here you can see you can have the water value like water availability. In water availability generally how do we mention in the storage values? What are the units for the water availability generally we MCM, BCM, TCM, TMC, trillion million cubic feet. So it's in power components. So that is million units. So what we do first, all the water availability values are different year values. First we get, then we keep them in a descending order. So once we keep them in the descending order, then using this I by n plus 1 formula, just a very simple formula. Using I by n plus 1 formula, for each row, for each serial number, you will get the dependability. So you can see there in the 18th value is coming at 50% dependability, the 27th value is coming at 75% and 32 value is 90% dependability. So can anybody tell which value will be higher? 90% dependability value is higher or 10% dependability value will be higher? Which value will be generally higher? You can see this table also. Yeah, 10%, because that is a very rare chance, right? Matlab, all the 365 days only 10% of time only that value will be available. Let's say monsoon values. Monsoon peak values can happen for only small amount of time, right? So that is why if you see the large dependability 90%, that means almost throughout the year the value you can see 47,000, whereas the starting values let's say 10%, you can see 95,000. So less dependability means that means less time it is available. So that's how we have to fix the particular water year. Like suppose if you are designing irrigation project, 75% dependable year is 1979 1980 data. So that data we will use for our analysis. So first you collect this data for so many years, like say 20-30 years, arrange them in the decreasing order, you will know the dependability values. For that dependability we will fix the particular year for analysis. You cannot simply take any value, right? To take particular value, this dependability is used. So like I told, for domestic, if you are designing for the domestic, that last value 35th 1992 93 that year particular value we have to consider. So all the water data for that months in that particular year we have to consider for our further analysis. So clear? So first we have collected our water availability. Next step is topographical information. So generally how do we collect topographical information? Survey. And what will be the instruments? How do we collect the topographical information using different instruments? Huh? Total station. Huh. Drones. Okay. So it's a site activity. So like you all told, based on the drone survey or total station and other any LIDAR survey, nowadays you can use the GIS, DEMs. So everybody knows how to delineate catchment area, how to develop contour maps also, right? So in this step we will develop contour maps and also river cross sections, and based on these two inputs, contour maps and river cross section, we will develop area elevation capacity curve. So that area elevation capacity curve, it looks like this, because suppose if you are planning a dam at any place, the dam will be, this is a vertical valley. If you are having a dam, suppose let's say 50-meter height, different heights, you should know what will be the volume of the reservoir. So for that, area elevation capacity curve is useful. You can see different elevations, we will know the area and also volume. You can see the graph. So for different elevations, one graph like the bottom one is showing area, and you can read the capacity from the top one. So the area elevation capacity curve is very important to know what will be the volume of the water reservoir and also area of submergence. So that how that will be useful in the next steps. And in this step we will also see new zero elevation. What is new zero elevation? What is new zero elevation? So to plan your filter or anything, so you should also know how much sediment will occur in this reservoir. That also you should know. So generally we are designing project for 70 years or 100 years or let's say 50 years also, right? So for 50 years, how much sediment will be accumulated in reservoir? At the end of the 50 years, what will be the sedimented elevation? This is called new elevation. So in the second step, we generally collect the topographical information. We will try to plot the area elevation capacity and also we will check. So these are all desktop studies. You can see the general values, right? 1.2 millimeter per square kilometer per year. These are all you can take it from publications. There is no need to go to any site activity or nothing. So that's why this is very important in the initial step. So you can estimate some level. This is called new zero elevation. So based on, because this will be our total live capacity, so we can use only this much of water because this will be completely sedimented after 70 years or 100 years or 50 years as per our design life of the project. So whatever we have to design will be this portion. So this portion of water only we can use it for our purposes like irrigation or hydropower or anything. So that is new zero elevation. Then, so we know the new zero elevation also. Then the next step will be what is FRL? Full reservoir level. So MDDL, minimum drawdown level. Yes. And what is power potential studies? Any wrong answers? Like try to tell whatever comes to your mind. What is the use of power potential studies? So now we have fixed new zero elevation, right? So everybody is clear about new zero elevation. So this we cannot use anywhere because it will be sedimented in this life of the project. So whatever utilizes in between these two. So power potential studies is nothing but just to find out the capacity of the hydro plant. If whenever you go to any hydro project, you have seen, right, the capacity of that hydro project is 100 megawatt, 200 megawatt, some projects may be 1000 megawatts. So how do they fix it? They fix it based on the power potential studies. So you can just go through this slide. I'll try to draw there. So you can just see on the screen. So what in power potential studies, like I told, first we have finalized on particular year, right, based on the dependability. So that particular year values, whatever flow values, we'll fix it, take it here, and we using the formula rho g QH, that is the power formula. So for different heads, so we'll first try to estimate what will be the power. So first what we see for different iterations we will do, like let's say suppose 12 megawatt, 14 megawatt, 16 megawatt, up to some 20, 30, 100 megawatts we will try to do, and based on this curve for different megawatts, you can see in the x-axis these are the different megawatts. So different megawatts, what will be the incremental energy? So based on this graph, wherever there is a sharp decrease, so that will be our optimum hydropower capacity. So to estimate this, we should have our FRL. So FRL, like I told, shall we wait? Or this problem happened yesterday also? Achha, okay. See, now we have evaluation, right? So now we should know this, what will be the FRL. So how do we fix? Like I told, for hydro projects, we use this power potential studies. Power potential studies is nothing but like, what is the formula for power generation? Efficiency into rho g QH, right? So Q we have finalized from our dependability value. What we have to, we don't know is H. So generally in power formula we have the formula, right? H is equal to MDDL minus tail water level plus 2/3 of FRL minus MDDL. So it this thing, right? At least provide some cushion. Exactly should not equal to at least provide some cushion so that we can have some intake structure. In this portion. So that is why some 10-15 meters cushion always we should give. So that will be our MDDL. MDDL we have fixed. Then how to fix FRL is different. If you fix FRL here, you will get some power, right? As you increase this FRL, so that is how you have to do different iteration studies, and also you try to give input, like you can, net head is there, right? So just this is the net head formula. For different FRLs, you just give the input here, these values will automatically change in the Excel. And I have shown in the next that for different megawatts, so we have to plot this graph. So we have to see for different FRLs, what is the total energy we are getting, like annual energy we have to check, load factor also, we have to see this graph also. These three factors decides how to fix this capacity of the hydro plant. If you are not getting at this moment also, no problem, just you should understand that power potential studies are required for hydro power plant capacity fixation, and also to fix our FRL in case of hydro plants. Same for irrigation projects, we have to do irrigation working tables. I think this was taught in the previous lectures, irrigation working tables. Yeah. So for each crop you have to find out what will be the water requirement. Like you can see that in November month, 10 days, it's easy to divide the values into 10 days so that we can do analysis in effective manner. So in the November month, what will be the water requirement per crop? Here it is, the crop is wheat. So for the wheat, what will be the field irrigation requirement and what is the gross irrigation requirement? These values we'll first try to find out. And same for different crops, oil seeds, wheat, gram, and what is the total demand in that particular November. So you can see the maximum will be, we have to consider. So 11.297, you can see here. So the peak 10 daily irrigation is 112.97. So we just add 10% irrigation extra, and you add drinking water if there is any drinking water demand also. So just sum it, and this is how you have to fix the canal capacity. So then, like I told, it is a 75% dependability, right? So you can see the S value. S means success. You can see this S. So this success rate. So different FRLs. Like if you assume FRL at this place, you just put all the values in this Excel, you will get this value. Either it is success or failure. It should be above 75%. Suppose we are doing it for different years, let's say you are doing it for 40 years, you should get that S value 40 into 0.75 times. So these many times it should give S value success. That's how you have to fix the FRL for different. Let's say for this FRL and for this MDDL, this is the volume of water we can use, right? So for this volume, let's say it is coming almost 20 years only success. So it is not matching this requirement, right? So now we have to increase the FRL, increase the life storage. Then again see it will increase up to 30 years like that. So that's how you fix the FRL in this step. Power potential studies for hydropower, irrigation simulation studies like working tables for agriculture irrigation projects. So we have fixed FRL, MDDL, new zero elevation, everything, etc. So next step is to go for geotechnical information. So why we are doing this geotechnical information at this step, not at the first step? Can anybody tell? Why can't we do at the starting geotechnical information? Because see, we have finalized FRL, right? So after this it will be maximum freeboard or 5 meters, anything less than 5 meters only. So we will try to, we will know approximate height, dam height, let's say H. So some investigation depends on the height of the dam also, because what is the geotechnical information? So you have to do some boreholes. So the borehole depth, sometimes it depends on the height of the dam. So if this is a valley, this is the dam. So generally we recommend at least 5. Out of 5, at the center of this, at the bottom of this portion, we will try to recommend at least one hole should go up to the full depth of the dam. So this height will only be fixed after this fixation of FRL, right? So that's how you have to do after this basic calculations. So in this step, so these are the different studies we do it in the geotechnical investigations step. So we will do geological mapping, we will do the drilling, then we will do the drifts, we will do the geophysical methods. So can anybody tell what is the geological mapping? Any answers? What is geological mapping? Yeah. See, in geological mapping we don't do anything. The geologist go to the site and just observe what are the features available. So just there is something, it is here, right? What is this? Anybody involved in geotechnical investigation till date? So this is geological hammer. It's just a hammer. So this is geological hammer. So all the geologists, it's a must for them. So just like we will be using our calculators, phones, right? For geologists, geological hammer is must. So whenever they go to site, in geological mapping I told, it's just a collection of field data. They don't do any drilling or anything. With just a hammer they will try to hit the rocks based on the number of blows required to fracture this rock or crack this rock, or to get the some small pieces. They will just use the geological hammer in this step. So geological mapping is just to collect the field data. They don't do anything extra. Then like I told, we have finalized the dam head, then we have finalized the location of boreholes and the depth of the boreholes. We will be doing the drilling. So these are the drilling setup. So we will be doing the drilling. Then drifts. What are the drifts? What is the meaning of drift? What is the meaning of drift? Boreholes are like they give only pointed data, right? Only information about this particular along this depth of the borehole. So sometimes it's very important to get the information in this direction. So for that and one on this bank. If your dam height is more than 60 meters, so at every 60 meter interval we will do one drill. Suppose this we will do at least one more drill hole. Interval should be 60 meters. So drift means nothing but manual excavated tunnels, small tunnels. And geophysical methods, what are the different geophysical methods? What are the different geophysical methods? You all know electrical resistivity test, seismic refraction test. So these are the investigations we have to do, and what will be the results? Results will look like this. So in the geological mapping, like I told, just collection of field data. So on the topographical map already we collected from the step 2, we will just plot it. You can see these are the different, earlier the topographical map looked like only contours, right, these lines, but now you can see triangular shape is there, some different colors. So these are the different rocks or different what is the overburden. So that symbols we will place on the geological mapping. So this is the first step. Then we have done the drilling also, right. So there this drilling, so based on the drilling we will get this core samples, borehole core samples, and in the tunnels, like I told, drifts we will be doing, like we will also get the total information about the geology in these tunnels, and also we will be doing some tests in the drifts, so that we will get some accurate data of the rock. And this is the geophysical method, like in the these are the different electrodes. So when you pass the current or seismic refraction techniques, you will get the different velocity profiles. You get this type of results. So everything is a complete different subject, you can explore on your own, but you should know different methods of the geotechnical investigations: geological mapping, drilling, drifting, and geophysical methods. So always recommended is to do some bores, drillings, and if the problem is severe, you also do geophysical. Compare these two, because like I told, drilling we will do at different locations only, right. So it gives only point data, but geophysical it can cover whole area. So it will, because what happens, you have done one drill hole here, but some particular information is missing here, right. So to get that information and to save the time, we can do geophysical and drilling, we can compare both results. So clear? We will be doing these 4 investigations, and results will look like this. And once we get these core samples, so there are some different tests. If you are collecting sample soil materials, so these are the different tests. And if you are getting rock samples, unconfined compressive strength, modulus of elasticity, and in the in situ, like I told, I have shown in the drifts, right, like in the drifts. So the in situ means at the site, whatever test we do it in the site. So these are the different in situ tests: bearing capacity, permeability. So in permeability test, generally how do we give our results, in what units? Permeability. Huh? Yeah, meter per second. Generally Lugian, whenever you hear Lugian means it's a permeability value, Lugians. So I think everybody has seen this geological log sheet. So these are all part of the geotechnical investigations. So the step 4, these are all part of geotechnical investigations. So we will do some investigations, and based on the investigation, these are the outputs, and when we get some samples, we do this testing, and that boreholes, these boreholes when we collect, right, the geologist will try to plot the log along the depth of the borehole, that is geological log. You can see here different, as we go down from the 0 depth to 3 meter, 6 meter, like this, whatever the conditions, first we got the overburden material, then we got weathered rock, then fresh rock, and also we do what is the rock quality designation, what is the core recovery, and the important is permeability value. You do some water test also in the boreholes. So this gives very crucial information for different analysis, even the seepage analysis, everything. These permeability values are very important. So these are the output of geological investigations. If you see some Tehri dam site in before the dam. So you can see after investigation, like these are the different boreholes. So they can able to plot different regions. What is weathered rock, more burden, fresh rock, etc. So once we finalize this geotechnical information, then next step will be design flood and diversion flood. So what are the different design floods? What are the different design floods we generally consider for our dams? SPF. What is SPF? So generally what will be the return period for SPF? Generally it is equal to 1000, generally 1000 years SPF, and one more is also there, right? Important. Probable maximum flood, PMF. So you all know estimation of PMF, everything right now. So this step we will consider, we will estimate the design flood, like all the dams will be categorized into three categories: small dams, intermediate dams, large dams. So based on these three categories, we will have to check what will be, we have to consider that particular flood. If it is a small dam, we can consider 100 year. If it is an intermediate dam, based on the above two criteria, based on the gross storage and hydraulic head, we just consider SPF or PMF. So we know the design flood values. Now, like in the first slide I have shown, right? For to pass the flood, we should have spillways. So there are so many spillways. In this step, we will finalize the spillway type and dam type. Like in the beginning only I told, my class will be continuous, right? Dams, whether it's concrete, earthen dam or barrages. For barrages also steps will be similar. In barrages also you should collect the water availability, topographical information, geotechnical information, and design flood. And based on the design flood, how much waterway you have to give. That is all. It's all same steps. So here, based on our spillway design flood, we will try to finalize different spillways, like whether it is Vogie spillway, shaft spillway or side channel. And also at this point, we will try to finalize the type of the dam also, whether it is a concrete dam or earthen dam, because we get the information of geotechnical, what is the rock available, rock characteristics there. So you can see here some classification how to select the type of the dam here. Like in the previous slide I mentioned, right? In this step we will try to finalize the type of the spillway and also type of the dam. So you can see here concrete dam classification and earthen dam classification based on different parameters. Based on your site specific, every project is unique project. You should not simply copy one project parameters to other project. So every project is a unique, like say northeast projects will be having some issues compared to the south projects and Himalayan north projects. So here the flood will be high. Generally, if you see in the Arunachal Pradesh and all this, the floods will be very high. So our spillways should have that much capacity. So if you see the length of the dam is the critical point. Generally concrete dams we allow it, we generally design it for low to medium lengths only. If the length is too large, like kilometers, you cannot have concrete dam, right? Unnecessarily it will increase the cost. When you increase the cost, the project will not become viable. So rockfill and earthfill will be very suitable if the length is more. Like if the design flood is more. In earth dam, what happens? We cannot keep so much. Like I'll show here. If the river valley is this much portion only, so if your spillway is coming, let's say this complete is 400 meters, if the spillway is coming around 200 meters, what will be the remaining length? 200, right? So in this 200 you cannot have embankment dam, because the connection between this concrete, this is called concrete, right? This concrete and this embankment connection also, it will be very big problem. So if the length is more, like if it is a plain area, the length is let's say kilometers, you can have central spillway, concrete spillway, let's say from 300 meters spillway or 200 meters, still we have so much area, 800 meters, more than kilometers, then we can have embankment. That's how you can plan. So next thing is diversion flood. So which value will be higher? 1 in 25 year non-monsoon or 1 in 100 year monsoon? Yeah. So why we take more value for earthen dams? Why? Why? Safety is okay, but why? Why only for earthen dams we are taking more value? Because we cannot allow overtopping of earthen dam, right? Earthen dam will get fail whenever the dam water level crosses the dam top. Whereas concrete structures it can take, we can allow some overtopping during the construction. That is why we take less values for the concrete dams. In earthen dams we consider 1 in 100 years monsoon values, because some projects like northeastern projects and even extreme north projects, where diversion flood is also critical factor to select the type of the dam. If the diversion flood is so large, but the preferable option is if it is earthen dam, but based on the diversion flood we have to go for the concrete dam only, because generally we cannot construct to particular level in one season, right? Generally in this extreme north and some harsh conditions, the time available for construction will be 3 or 4 months only. In the 3 or 4 months you cannot complete up to particular level. Again the flood will come and this completely it gets overtopped. So that's how sometimes in some particular project diversion flood also plays a crucial factor in deciding choice between concrete dam or rockfill dams. And seismic. So if earthquake is the only criteria to decide, then we better go for rockfill dam, because it can take up to 10 to 15% damping. So that means damping means it's energy absorption. So damping means energy absorption. It can take up to 10 to 15% of energy absorption, whereas concrete dams it's a rigid type, right? So it might get crack in that earthquake activities. Whereas the foundation, this is again one more important criteria. Concrete dams, we always place concrete dam on the rock. So natural ground level, it's after some depth you will be having this rock. Concrete dam we always place on rock. We never place concrete dam on a both burden or a feathered rock. Concrete dam we should always place on fresh rock. Whereas earthen dam, we can place it on weathered rock also. The overburden is also sufficient to take the strength, because in some dams we will not get fresh rock even 100 meter depth also. So what we have to do there? We have to go for earthen dam. Like many dams are there, like in Polavaram, there the depth of the rock is 80 meters. So we cannot exploit 80 meters, right? Even the latest that failure Tista 3, there the rock was around 60-70 meters. That's why they have gone for the CFRD. CFRD, rockfill dams, earthfill dams, everything comes under same category. Concrete and these are all different. So there they have proposed CFRD. Now everybody knows, right, what happened to Tista 3? It got washed away. So because of that reason, that time they have adopted the earthen dam, rockfill dam, but now they are going for the concrete dam, because like I told, now the design flood is playing crucial role there. So that's how you have to select the type of the dam. So like I told, different spillways, I will just quickly go through these different spillways. So I have already told these are the first thing, varies for small discharges you can go for the ungated discharges. So further improvement we will be having some Ogi spillways. So you can see the gates at this position only, okay. So whenever the water reaches above the crest, then only the water pass from the spillway. Then to improve further discharge, these are the photos at the different dams, Parwan dam side photo. So earlier, like in the previous image we have seen the gate was at this place. Now we have reduced, see this is sluice spillway. So we have taken the gate to the further down. What is the benefit from this? In this image you can see the gate was at the higher level, but whereas here the gate is at the lower level. So why we have considered this option? Any other reason? Sediment also, we can remove very easily from this. Then what is the main advantage if you take down these gates to lower levels. Any wrong answers also? Because like discharge is directly dependent on head, this H, right? If you that formula Q is equal to, what is the formula for the Voge spillways? So it is directly proportional to H. As the head increases, the discharge also increases. To increase the head on the gates, or to increase the head on the crest, so as you take down, the head also increases, so flow will increase, the discharge will increase. So this is the main advantage of taking down the gates from higher positions to lower levels. So this is sluice spillway, orifice spillway also you can call it as. Then one more spillway, side channel spillway, where it's just like Voge spillway, but like I told, in earthen dams, if the width of the valley is very narrow, you cannot have spillway and also dam, right? So that's why they will have spillway and the separate at the end of the abutments, or you can have some projects, it will be completely on the separate place. So in some we'll be having some shaft spillways, like you can see in theory, they have provided this shafts also. Like if you see in the plan, in the river flows, because now it is completely rockfill dam, right? There is no overflow, so the water enters into the tunnel and goes through like this and goes to the outlet here. So if you see the images, so as soon as, because it is ungated, you can see, as soon as the water goes above this particular level, the water automatically falls into this tunnel and it gets into the outlet. This is a tunnel spillway. So like different spillways I have shown you, right? Ungated, from ungated to Voge spillway. In the Voge spillway we cannot take sediments, and also the discharge capacity will be less because the head is very less. Head is only this much portion only. So to increase the further head, we will take down this gates to further lower levels. This is side channel spillways, shaft spillways, and very small discharges or small purpose, we will have some siphonic spillways based on the siphon action. Like you can see this shape of this. So it is having some constraints like 10 meters up to 10 meters. You should just explore on your own what is the siphonic action and what are the limitations on this. So everybody is going right, getting all this right. And if you have any doubts, you can ask me. So we have completed all this, we have finalized the dam type, everything. So what are the remaining things? We have completed this investigations, we have completed the new zero elevation, we have finalized the MDDL, FRL based on the flood power potential studies and irrigation simulation studies. Now we have to fix the dam top, right? How much dam top we have to keep. So to fix the dam top, we have to do MWL. Any wrong answers also, no problem. Just this is our FRL. So this is our MWL. So can anybody tell what is the difference between FRL and MWL? Why FRL and MWL comes? Why maximum water level comes in a project? No. Any other answer? See, freeboard is above this levels, water level. This is freeboard. Okay. This is also freeboard. This part also sometimes we can include in freeboard. But what is the major difference between FRL and MWL? See, like selected these different spillways, right? suppose there are some, like I told, if you have enough river width, you can have the spillway capacity equal to inflow. But if you don't have, like, see, this is the river width, but here the width is very less. But in the both cases flood is same. You cannot see this much width. You cannot allow you can maximum allow spillway only. If the inflow flood is, let's say, 10,000 cumex, here you can able to provide 10,000 cumex equal spillway capacity, but here you cannot. Here suppose, let's say, 5,000 only. Let's say you can able to pass only 5,000 cumex from the spillway. So what about remaining 5,000? So it will try to accumulate in this dam, right? Because the inflow flood is 10,000, you can able to pass only 5,000 from spillway. So that try to accumulate in this reservoir. So there will be some increase in reservoir level above FRL. So that maximum level is called maximum water level. How much maximum? Because you all seen this graph, right? Hydrograph. You all seen this hydrograph. So based on this hydrograph, as this hydrograph passes through this, what will be the maximum water level achieved? That is called MWL. This is only happens when there is a difference between inflow flood and spillway capacity. When you are providing inflow capacity equal to outflow capacity, then there won't be increase in the water level. So whenever there is a spillway capacity is less than the inflow flood, obviously there will be some increase in the water level, that is we call as MWL, maximum water level. So that we do it by some flood routing studies. Same method, inflow minus outflow is called storage. Same formula, I am just mentioning here because of the time constraints. Because this class generally I take it full day, like 4 hours. But in this class I have to cover this barrages also. But I am giving these slides here. You can just go through this steps. Very simple steps. Like concept you have understood, right? Inflow is coming. If the inflow is more than the spillway capacity, obviously there will be some increase in the water level. So how much water level it will increase? So it's a very simple plus and minus type only. You can see. I'll just. If you just go read about this modified pulse method, the inflow minus outflow is equal to storage. That is the concept. So we will try to first prepare the tables. What is the storage values at different elevations? What will be the outflow at different elevations, and what will be the inflow values? You can see the inflow value in that column, and outflow. So there is some method. It's a very simple method to estimate, because there will be so many unknowns, right? So when you go to this modified pulse method, so you will get this graph. So this is our inflow. You can see the reservoir our routing will look like this. So there is reduction in this peak value. Actually what happens? Your inflow is this much. Everybody previous classes. So this is our inflow hydrograph. Like I told, outflow it's only restricted to 5,000. So the outflow graph will come like this. But what about this volume? This volume was observed in reservoir. So that is how this water level increases. That we will find out from this step, maximum water level. So in this you can see the maximum water level value also. We will give maximum water level attained 43.36. Peak rate of inflow you can see 2,500, and outflow you can see 2,300 only. So whenever inflow and outflow are not equal, there will be some rise in water level, that is called maximum water level. So almost we have finalized everything, FRL, MWL. The only thing remaining is freeboard. So we have dedicated code for freeboard calculations, IS 10635. So if it is, this is a dam, so this is called fetch. Freeboard is basically because of the wind. Due to wind there will be some waves generation, right? Waves generation, all those things. So to estimate, because wave can happen in any direction, right? So to get the average, so there was a fetch development, 45 degrees this side and 45 degrees. It's a complete method is given in this code. Please try to go through this code. It is covering both the dams, concrete and earthen dams. So developing of this fetch and steps given in the code. So these are the steps given in the code. So you can see it is covering both embankment dam and concrete dams. So first you have to estimate the pitch and different wind speeds based on the location and simple calculations. So you will estimate the freeboard required at this step, and based on the freeboard just add this to the our water levels. So that will be a top of the dam. So you can see here there are two freeboards given. What is normal freeboard and what is minimum freeboard? Any guess? What is normal freeboard and what is minimum freeboard? Any guess? Any guess also? See, what is FRL? Actually, by definition, it is by name it's full reservoir level. But what is actually it represents in the site? FRL, full reservoir level. That means full reservoir level means when the gates are closed condition, we are maintaining the reservoir at particular level throughout the year. Let's say there is no spillway, there is no spill from the spillway. So that level we maintain it as FRL. Okay, that means there is no water. So this is our general case, right? Almost most of the time we follow this condition only. During the monsoon or excess floods, we will open the gates. If the capacity is less, then obviously there will be increase in the water level. So FRL to this dam top, this difference is the normal freeboard. The difference between MWL and the dam top is minimum freeboard. Normal freeboard is corresponding to FRL. Minimum freeboard is corresponding to MWL. So whatever calculations we do, like the freeboard we have obtained, right? Here freeboard required. So we just add freeboard, normal freeboard to the FRL, minimum freeboard to the MWL. So then we will get the top. So maximum of these two we will adopt as a top of the dam. And what is the difference? Then you are doing the calculations, all the steps are similar. What is the difference in both this? See, what is the difference in both these calculations? The difference is wind velocity. You can see in the normal freeboard we take maximum more velocity. We are reducing it to 2/3 in the MWL calculations. You can see 150 and 100. That values in the second step you are seeing, right? In the normal freeboard we are considering 150 meters wind velocity, whereas in the minimum freeboard we are considering only 100 meters. Because MWL, like I told, it's a very rare condition, like in the monsoon season or whenever there is a flow. So that's how there is no need to consider. See, the basic design philosophy is like you should not consider two mutual exclusive events. Like you should not consider earthquake and high flood at the same time. Whenever you design any project, you should not consider PMF plus earthquake. So that is that will not exist actually. So you should not design for that. So that based on that criteria only. In the normal condition, that is a regular condition, that's why we are taking maximum velocity of that area, wind velocity, and we are reducing it to 2/3 whenever we are considering MWL calculations. So that is the basic difference only, remaining steps are all same. So for which dams we have to give more freeboard, concrete dam or embankment dam? Which dams we have to give more freeboard? Why? Because earthen dams are generally more chance of failure, right? Because if you get less, as soon as the water reaches the dam top, earthen dam will fail. So that is how earthen dams are, we are taking the more diversion flood and also more freeboard. Because you will not see the difference here. When you see the code, the minimum value for earthen dam will be 1.5. Minimum value for concrete dam is only 1 meter. So we have fixed the dam top, everything. Now what will be the next step? Stability. So if you see this concrete dam, even if it is earthen dam also, section we have almost finalized, right? So this is our top level, this is our bottom level. So what we have to do now? If it is an embankment dam or earthen dam, we have to do the stability analysis. to finalize the slopes. So we have to do the stability calculations. So why we do these three stability calculations? Why do we do this sliding, overturning and stresses? No, for failure only, but what is the difference between these two? Like I have clearly mentioned here, slope stability for earthen dams, whereas this is for concrete dams. In concrete dams we do sliding check, overturning and stresses check, whereas in earthen dams we do slope stability for upstream slope and downstream slope separately. In earthen dams we don't check for the sliding stability. Okay. Then once we have finalized, just I will. So these are the 10 steps. You can add further steps also. You can do some parallel steps also wherever needed. Not necessarily to go by step. Wherever you can do parallel steps, you can do. But the idea is to get the dam level, get the dam height. Then only you can go for the dam stability analysis. So if you see earthen dam. See, this is earthen dam, right? So this is concrete dam, this is earthen dam. The difference is that the stability analysis we do sliding for the concrete dam, whereas this earthen dam we do slope stability for downstream slope separately and upstream slope separately. And in the step 9 energy dissipation, suppose whenever this water is flowing this way, so we should have some dissipation arrangement, right? Otherwise it will erode the downstream area and it will create a problem for the dams. So we are having different types of this energy dissipation, stilling basin and bucket type. So can anybody tell hydraulic jump happens in which kind of arrangement? Hydraulic jump happens in stilling basin or bucket type? Hydraulic jump. Hydraulic jump happens in this is bucket and this is in which hydraulic jump occurs. So hydraulic jump means like the initial depth will be less, after depth will be more to match the water. So the water gradually tries to attain this based on this hydraulic jump. So that stilling basin is nothing but hydraulic jump. Whereas the bucket, the water will like form like a ski jump. So it just leaves from here and try to hit at some different place. Let's say if the dam height is more than 100 meters, it vary up to 100 meters. Just like a ski jump. So stilling basin, hydraulic jump calculations are there. In bucket, we just calculate throw, how much distance, after how much distance the water is falling. So after that we will do some other analysis, like we will do gates analysis, foundation treatment, anything. So these are the different softwares also we can use for different steps. Like you have already used I think GIS, Hex softwares, and in AutoCAD we will generally use it for development of river cross sections, contour maps, area elevation, capacity curve, everything. And GIS I think you have used for estimation of design floods. And HMX can be used for this finalization of MWL, that modified pulse method I told, right, how much water level increase. And stability calculations you can do it in Abacus, Midas, GeoStudio and RockSense, all this. And any structural designs you can do it in STAD. So this is complete designs. So this you can adopt these same steps for earth dams, even barrages also some steps applicable. So just I will go ahead. Any doubts up to till this place? From now onwards we will go different case studies or thing. Clear? So some case studies, like you can see this is a project layout. So in the project layout you can see when you do the geological investigations, you get to know that only this green portion is the only good rock. So your project layout should be such that you should plan in that particular area only. See if you see the cross section also. So these are the challenges you encounter. So this is a weak rock, this is a good rock. So this junction is also very generally contact between good rock and what you call weak rock will be always a very shear zone type. So this also we have to consider. So in project layout or like deciding, you should consider all the geotechnical data, and also like you can see the stilling basin, like the water when these are the spillway blocks, as the water goes down like this. So either you can have the stilling basin, because like I told in the ski jump, water will try and go and hit at some more depth. This is 200-meter dam, so the ski jump was going up to 300 meters, but you can see the contours, it is completely hill. So you cannot excavate full hill, right? So there we have adopted different solutions. So here stilling basin we have adopted. So that's how you can plan the different layouts. So even you can see the spillways. So there are some issues with the different countries. Like, let's say if you are dealing with Indus issues, with the Pakistan Indus issues, there at that time Indus treaty was there. So there the question was that they will not allow to take the spillways to lower levels. They always want this spillways at the higher levels. So like you can see, our discharge is more. Like I told, why we take down the spillways to the lower levels? Because of the head, the discharge is more. We want it will be taken down, but they want no. You should not take. You should keep higher. So that's how you have to plan the layouts. So the issues will be many. Like each project will be unique. Some project will be having geological issues, like this water projects, like with the especially the Pakistan that time. Indus water treaty issues will be some different. Like this photo that was I explained. This was a masonry dam. The issues with the masonry dam was like it was a old concept, and every joint you can see the leakages. So can anybody tell what is this dam? Project? So this is a Polavaram dam. Like you can see the length of the dam. The discharge was so high. Earlier it was just like this was a hill only. But here the depth of the overburden is up to 80 meters. The rock is not available even up to 80 meters. So the option is only to construct earthen dam. So the main dam portion they are constructing earthen dam. Then what is how to pass the flood? So they are completely excavated this hill area. You can see the spillway here. So the water will go now. And the earthen dam will be here. But here also they could. There are so many issues with regard to the construction. So there are some guidelines, not restricted to this. There are other many useful codes, and this is our DPR guidelines, CWC guidelines only. Here you can see what are the different topographical surveys extents, like how much intervals area data you have to collect, how much depth of the borehole spacing, and other chapter related information. Everything is there in this guidelines on Ministry of 2010 DPR guidelines. You can download it from the CWC website. I will just try to skip this step because I already explained, because whenever to finalize the dam axis, you always explore different dam axes. Suppose in this case they have identified 5 different axes. For each axis you have to estimate pros and cons, advantages and disadvantages, and based on that you have to finalize one particular axis. If needed, you have to do some investigation like boreholes at 2-3 different alternatives, because based on the topo, just on visual inspection you cannot able to differentiate, right? In that cases you can just do 1 or 2 boreholes on different axes. That will give fair idea to select one axis. So this also I explained, whenever there is a length, dam length is there, that we have to prefer that, like the last one. You can see this layout. This is Upper Siam, one layout. You can see the complex layout. tunnels are going, power tunnels. In this left bank also, right bank also, these are the diversion tunnels. Whereas see, same project, that was a different axis, this is a different axis. You can see the simplified layout. So which one you will prefer? This one, right? So many issues will be, because here you can see you are excavating tunnels, you are placing tunnels in both the banks, left bank, right bank, and diversion also is a big issue. Diversion also you can see you are going through both the banks. These are diversion tunnels. Because during the construction, we generally, like I told, what are these? The small coffer dams. Coffer dam means there are the temporary, like you want to have a dam here. We just have small dams here first, here and here downstream, so that we will completely isolate this area to have this clear working area. So these are called as coffer dams. So now divert this water through these tunnels or channels, anything. So you can see if you want to have this main dam, there are small dams, these are coffer dams. So now the water is diverted from here. You can see the downstream coffer dam also. So now this area is completely water free, so we can have construction. But the layout, you can see the diversion tunnels are on the both banks, whereas this layout, simple layout, right? Dam is here, everything is on this side only. So that's how layout finalization is also very crucial. So this is one simple layout of hydro project. In hydro project, we will be having dam, we will be having HRT. What is HRT? Headrest tunnel. So headrest tunnel, then surf shaft, then power house. This is a general layout. This is what you call network of irrigation project layout. So that was the hydro project. This is, so we will have dam here, we can have some canals, and we will have some distributaries. So these are the different project layouts. Can anybody tell what happened here? Why the dam is overtopping? Water is overtopping over the dam. See, the main water has to go through this spillway, right? Here the water is not coming, only water is flowing all remaining portion, because the gates could not be opened. So you can see this next photo. This access was completely washed away during the floods. So they cannot go to the gates portion where they can operate the gates. They can switch on the motors or DG sets. So that was happened. So one more, if you see, if your spillway capacity is very less, nowadays what happens? There was so much increase in the design floods. That is why dam safety guidelines recommends that every 10 years you should revise your hydrology. That means PMF, revision of or updation of PMF. So this was Tista 3, like I told, right? Earlier the dam was, it was like this. You see, after the incident, complete washed away, this CFRD. So this is one more dam. This is Subansiri dam. Subansiri, I think everybody should know, Lower Subansiri. So in Lower Subansiri, this dam was completed, but just before the initial filling or something, this complete left bank is, you see, complete slided. You can see this big cavity is formed in that left bank. So now they have treated, now it's again they are ready for the filling. So these are all issues you have to consider. One is layout, geology, any sliding issues, or foundation, like in the Tista 3 case, if the design flood is more like Glop, glacier lake, outburst flood. So these are all issues you have to consider to select the type of the dam. So we'll just quickly go through this embankment dams. So like I told in the first slide, these are all same, it comes under the design philosophy will be same for all this type of dam. So you can see 4 major classifications. So earlier we have started with the homogeneous earthen dams, right? Because in the earlier days, whatever available material, we just made the dams using that material with some drains. So further improvement what, because as we are increasing the dam heights, so this homogeneous materials sometimes it got failed. So further we have updated it with the core materials. So we at the center we placed with the core material. So we have reduced the seepage. Then further nowadays completely shifting this core to the upstream. It's not core, it's a concrete facing or a geomembrane facing. So this is a still this is still in, it's a very better option, but like I told, if you cannot get core in some areas, core means clay material. These are all low permeability material, right? So clay material, if there is a very shortage in clay material, so you can go for the CFRD. The Tista 3, yeah, like you can see here, this was a rockfill dam only, but in the starting it is concrete panels. So while selecting, designing of this embankment dam, these are the different components you have to check. I'll just go through. We'll come back to this concrete dam stability again. What is the break? I told this is just 10 minutes break, we'll meet again. Okay, 10 minutes, in 10 minutes we'll meet. But like I told, man, I have so much to cover actually. So we'll meet at 11:35. I think tea is served here or you have to go there? 11:30. Okay. Then I'll just try to see. So this is embankment dam, right? Like we need this clay core. So sometimes we need this cutoff also. Okay. This is cutoff trench, and this top layers will be riprap. Riprap means nothing but big boulders. Why riprap is required? Because in this water side always there will be some waves, all those actions, right? To prevent the erosion, we will be having some big size boulders, ripraps. Even if it is required in the downstream also, we can provide, or else we can leave it also. And this is shell materials. So in simplified manner, I am saying like slope protection and surface drainage. This is a riprap and everything, and core and casing. So this is the core material, core, and this is the casing. And the design consideration, like I told, we have to again check for the stability. This stability and settlement. Concrete dam generally it will not settle, but embankment dams it will settle. So settlement analysis also we have to see. So two important criteria I will tell how to. You can see the image here. See, if you just give the dam section like this, water is up to here, obviously seepage will occur through like this is a hard rock. Let's say this is a hard rock. This is overburden only. OB means overburden. So obviously overburden is permeable. So water will seep like this. If you don't give any to this thing. So if the depth is okay within the limits, either you can extend this cutoff. Cutoff means nothing but again filling with the clay. Okay. This is this we call it, if you are taking this cutoff to the full rock level. So this is called positive cutoff. If the rock is at this level, Like I told, excavation complete depth is not possible, right? Even cutoff also it's having limitation 10 meters only, maximum 10 meters only you can excavate. So remaining, you just have to do the grouting. So this is called partial cutoff. So these are the basic two differentiation between designs. You can see in this image, the impervious stratum is very at the higher depths, so that is why you have extended this clay core or cutoff to the impervious stratum. So this is called positive cutoff, like you can see in the name. Whereas the next step you can see, the rock is at the very lower levels. So you just extend this cutoff up to some depth, so partial cutoff. And how to reduce the seepage? So you can see, just focus on this portion and also this wells in the previous image. So in this image you can see there was no extension of this cutoff, right? Clay on the upstream side and there was no well here. Whereas in the partial cutoff, you can see there is a well here and also we have extended this clay material, so that to reduce the seepage quantity. So in this case what happens, there is no barrier here, so seepage will go like this. So whatever seepage comes here, it is collected in this relief wells. This is called relief wells, and we have increased the seepage length also by placing this blanket upstream. So the water will pass like this, so that seepage head also will reduce. So these are the basic two things you have to consider first. First, either you are going for the positive cutoff like this, or just extending this cutoff up to the impervious stratum, or just you are giving like upstream blanket and relief wells arrangement. So these are the basic two design criteria for embankment dams. Clear? If you have any doubts, just ask. So how do you get this impervious stratum details? What's the depth? How do you get? How do you get the details of this depth of this stratum? Based on investigations, boreholes. So once you completed the boreholes, you will get the information about this depth of these things. If the depth is within the limits like 10 meters, you can extend this cutoff like this. Like in the Polavaram case, it was like 80 meters. So I will explain that also. So further, you have to do the seepage analysis also. So these are the basic two design differentiations. Remaining all is similar, like doing the stability analysis, upstream slope, downstream slope is same for all the earthen dams. But the seepage analysis you have to do. You can see the different cases we have done. Like you can see clay core is up to this level, clay core like extended up to upstream blanket, and complete like a full diaphragm wall type. So in this case what happens, if the dam height suppose let's say 50 or 60 meters, obviously there will be some seepage. So sometimes water is a precious thing, right? We are planning a water dam for some like less to store, to irrigate, to hydropower, but your entire water is going through the seepage. So that's how what we do. Sometimes to arrest the seepage, we will be having complete blanket diaphragm wall. You cannot extend this clay core up to this level, but what we can do, we can have 1 meter thick, we can excavate, we will fill with concrete. So that is called diaphragm walls. So that's three options we have studied here. In the first option, no any treatment, what is the seepage? So again you have to do the some what you call check based on your value of the water and also quantity of seepage, and just extend this blanket. What is the seepage quantity? Even the seepage is still more, just complete cut off using that 1 meter thick diaphragm walls. So this is that. Can anybody tell what is this software? Anybody use this software? GeoStudio. So this is in GeoStudio, this is in RS, this is in Slide. So like I told, if the what you call depth of the, in that cases if you want to provide complete seepage barrier, so you have to give this what you give? You have to give the diaphragm walls. So generally that is 1 meter thick. So to have 1 meter thick, we will have to excavate. So how to excavate? So like this. So you should have this. This is the dam axis. So in the you can see the center. So along the length, it will excavate 1 meter width. It will excavate, and you can see it will fill with the cement slurry. After which you can see, matlab. So that will block the seepage. So basic thing is to go for the positive cutoff or partial cutoff or the seepage measures like this. So one more, like sometimes what happens, the diaphragm wall, I will just. So this is the diaphragm wall we have made, right? Sometimes you can have this high pressure seepage pressure grouting also. This is called jet routing. So jet routing, it will make a columns like this. The nozzle, it will rotate with the high pressure, and it will form a columns like this. But there is a limitation. Diaphragm walls you can go up to 130, 140 meters. You can go up to 60 meters, and also it depends on the stratum. And this is soil columns. In the soil columns also, it's like circular one only based on the chemical treatment. It will mix the soil and make the columns like this. So these are the jet routing columns. These are the soil columns. These are all to reduce the seepage. So soil columns generally we can go up to 30 or 40 meters only. So that's how you have to select the type of the treatment also. Why we have to select? First you have to do the seepage analysis like this. You have to estimate the seepage. If the seepage is within the limits, then there is no requirement of any treatment, but you have to completely protect the seepage. Then you have to do either this diaphragm walls or jet routing or soil columns. So break needed, some 10 minutes. 10 minutes because we'll be covering barrages also, right? 11:45 we'll meet.